Hey guys, what's up? Welcome back to Two Men One Chorus podcast. How you guys doing? Well, good to see you guys again. I'm having an amazing day, and I hope you are as well. And today, oh, by the way, I need to tell you. So, thank you very much for supporting us. And without you guys, we wouldn't have made it this far. So, second episode, second season, everything is going great. Yay! So today we are trying to keep it short here. So we're gonna get right into the detail. I'm gonna teach you and tell you what you need to do for the lab, this coming lab, okay? And all the calculation involved. What you're going to need is you're going to need a scientific calculator, not from your phone. Just get used to using it, and your computer, a laptop that has Excel. Okay, if you have a mouse, it will save you a lot of time. Okay, so I'm going to teach you how to plot graph. All right, let's get into the detail right here. So today, this lab, you're going to determine the concentration of phosphate in a water sample. Right, we take it from Mississippi River, and I use a spectroscopic method. Okay, as some of you probably have heard the word spectrophotometer or spectrometer. We're gonna use that. Okay, all right. So let's start it right here. So all the mineral in water. You guys know water has a lot of things dissolved in it. We're gonna focus on the mineral in water, especially the nitrogen as nitrate. Okay, nitrogen is essential to production of plants and animal tissue and used for synthesized protein. I think you know that is in biology. Phosphate, on the other hand, is also important, right, for converting sunlight to usable energy and for help cellular growth or reproduction. Really important. But too much of the good thing is not that good. I'll take a look right here. This is what happened. Eutrophication, I think that's how they say it. So it's an excessive amount of phosphorus and nitrogen, or phosphate and nitrate in water. So too much of these minerals speed up to uncontrollable um, what's it called? Growth of plant life, for example, algae. And the uncontrollable plants deplete the oxygen in water, and that causes all the marine lives die, basically. Okay, so for this is really important. So the U.S. Environmental Protection Agency, so U.S. EPA, say that the water sample from river cannot exceed, say it wrong. No, the phosphate level of a water sample cannot exceed 0.050 milligram per liter or part per million. You probably have heard this word before, ppm. Okay, so we can't exceed that. And we can take a look at it. So in New Orleans, we have a Mississippi River right through us. We're gonna take a look and measure the concentration of phosphate level in this water sample. Okay. All right, but here's what we're gonna do. So a little bit problem here. So phosphate solution is colorless, has no color. How are you gonna measure the concentration of it? Well, we have to make it colorful by adding a compound, a solution called ammonium molybdate. Okay, molybdate or molybdenum can react with the phosphate from a complex called molybdenum blue. Looks something like that. Depends on concentration. Okay, so it looks something like that. You're gonna take this guy, put in a cuvette, and add in onto the spectrophotometer or spectrometer and measure the absorbance. Okay, we're gonna talk about how to use it in a little bit, right? But basically, this is what you're gonna do in this lab. All right. Now let's talk about spectroscopic determination of concentration. You probably have learned from lecture, especially in Gen Chem 1 maybe, that the transition state, transition metals. I say it wrong again. No, the solution of the transition metal show a different color because they have different oxidation number, and it's all really colorful right here. Okay. All right, we're gonna focus on the chromium 3. Right, the chromium 3 solution is green, look like that. All right. So let's say you want to measure the concentration of chromium solution. What do you have to do? Let's talk about this light absorptivity real quick. Okay. So chromium 3, of course, they got some electron floating around, like around nucleus, whatever. You guys know that. All right. So this electron can absorb light. Right. This electron will become excited and then release energy. This energy gets to our eyes, and our eyes see, oh, that's green color. Okay, the higher concentration of chromium 3, so of course more electrons in the solution can absorb more light, so higher absorbance, and release more energy. So you're going to see the solution is darker, looks something like this. Okay, so there's some examples. So low concentration and then high concentration, really intense green. All right, let's say you have a chromium 3 solution, but you don't know its concentration. This is what you can do. You're going to put this solution in a cuvette, look like this. This is a cartoon version of cuvette, and put in the spectrophotometer. It's so hard to say. And read the absorbance. Okay, the absorbance is follow Beer's law or Beer-Lambert law. Absorbance equal to molar absorptivity times length and times concentration. Okay, the length of the cuvette is 1, so always L is 1 centimeter. Okay, all right, let's say if you want to know the concentration, right, you need to know the rest. I'm saying one more time, make sure you get this. If you want to solve for, if you want to know the concentration of a solution using Beer's law, you're going to need to know the rest: absorbance, molar absorptivity, and the length. Okay, the length path here. Absorbance, put in the spectrophotometer, you get the absorbance. Molar absorptivity, well, we don't know it. We have to go figure it out. And length is 1 centimeter. All right. So basically, we're doing this to find concentration. You're going to need to find the value of the molar absorptivity first. Okay. And to do that, we call it calibration curve. You're going to plot a calibration curve. All right. All right, how do you generate a calibration curve? This is what you're going to do. You're going to make several standard solution. And when I say standard solution, means the concentration that you know, the solution that you know the concentration, right? If you think about a titration, the standard solution is the one in the burette, okay? All right, so we make a standard solution of chromium 3. So let's say I'm just make up the number here. So let's say 1 molar, 2 molar, 3, 4, and 5 molar. Okay, we'll take each one, put in the cuvette, and then read the absorbance in the spectrophotometer. Okay, and let's say you read it and it go like you can plot it: absorbance on the y-axis and concentration on the x-axis. Now, so 1 molar, you get some absorbance. 2 molar, of course, you're gonna get higher absorbance. 3 molar, higher absorbance. 4 molar, 5 molar, higher and higher absorbance. You're gonna have plot graph like this, right? Absorbance on y and concentration on x-axis. Okay, you can find the slope of it. I'll take a look. So it looks like a straight line. You know, if you look at the equation, A equal to eta, that's molar absorptivity times L times concentration. This actually like a linear equation where y is absorbance and x is concentration. Okay, it looks like a linear equation, and the slope right here, M is slope. The slope of this Beer's law is molar absorptivity times length. That's the slope. And if you still remember, what is the length of a cuvette? It's 1 centimeter, so L is 1. Basically, the molar absorptivity is the slope. Okay, so we call this generating a calibration curve, and you're going to do this in the lab. All right. So at this point, you know. Now go back to an unknown concentration of chromium sample. Right? We did absorbance and we find absorbance, so it's 0.2. So we know the value of absorbance. Molar absorptivity. So we just did it together right here. So that's the slope of the calibration curve, and the length path length is 1, and so for the concentration. That's it. That's pretty much the whole lab. You're gonna do something like this. Okay. All right. Before we move on to the real situation, we're gonna simulate the situation that you'll be doing in the lab. Let's talk about our sponsor of this podcast. All right, if some of you have watched this video, take a look right here. And aw, a dog. Why are you leaving me this time? All the delivery, no delivery fees. Dash Pass. Anyone use DoorDash? Yeah, it's pretty cool. Actually, that hold on. Okay, hold on. Up. Okay, that video was as an ad for a Super Bowl ad. So and you will see like every year the Super Bowl ads always have dogs or some certain type of animals in it, and people love it, and I like it. So all right, anyway, so let's simulate the real situation that you'll be doing in the lab. Okay, so we're gonna give you a water sample. Hopefully we can get the Mississippi River sample. All right, depends on its availability. So anyway, so you're going to have one or two water sample, and you're going to need to determine the concentration of phosphate in it. All right, now the problem is, again, phosphate solution has no color, so you have to brighten it up. So add color into it by react with ammonium molybdenum solution. It wears for about 10 minutes. Okay, and then you're gonna get like a molybdenum blue solution. Look like that is really intense dark blue color. You're gonna put this, some of it, it's just like, I think probably 1 to 2 milliliter, maybe 1 milliliter, put in a cuvette like that. Don't add it too full, otherwise it's gonna go everywhere, overflow, and you have to clean it up. And if you put this in the spectrophotometer and you mess up the spectrophotometer, well, we will have a problem. So don't add it too full. All you need, just add it high enough that the light path goes through it. That's all you need. Okay. All right. The spectrophotometer that you'll be using looks like this. All right. So you have a monitor, we have a knob, we have all the button. You can the button right here. The sample holder is right in the middle right here. You can open the blue thing right here. So open it, you will see it. Sample holder. Okay. Put a cuvette in, close the sample holder, and then you just read it. Oh, take a look right here. All right. First off, the molybdenum blue absorbs light at 880 nanometers. So you have to turn the knob to 880 nanometer. And then you read. It will just automatically read it. Right. So 0.22. Okay. So, all right, 0.22, that's it. Absorbance of this solution. Okay. And you can guess that if there are more concentration of phosphate in water sample, the blue color is going to be more intense, basically. Okay. All right. Now, if you want to calculate the concentration of phosphate of this sample, this water sample, right, concentration right here. So you need to know the rest. Remember that absorbance is 0.22. We just read it right there. All right. Molar absorptivity. We don't know it yet. We have to figure it out. Length. Well, it's the length of the cuvette is 1 centimeter. That's it. And concentration. Okay. So you have to go find the molar absorptivity of the molybdenum blue. And to do that, well, we have to make a standard solution. Okay, you're going to make 6 standard solution. So I'm just make up the number right here. So let's say 0.2 millimolar, 0.1 millimolar, 0.05, 0.025, and 0.0125, and one more at the bottom. Here we go. So 6 of them. All right. Of course, none of them have color. Right? It's just phosphate solution. Right. Phosphate solution has no color, so you have to react with ammonium molybdate with 10 minutes, so you're gonna see all intense blue color like this. Okay, so note that I intentionally make the blue color is fading down here, right? Just low concentration, so lighter blue, right? High concentration of phosphate, so make it intense blue. If you know Sydney, one of your TA, okay, if you know her, so Sydney have done this 3 or 4, maybe 5 times already. I asked her to try it out, and that's her the water sample after adding the ammonium molybdate. Okay, so high concentration to low concentration. Look at right there. All right, this right here, this solution is the molybdenum coloring reagent. So she mixed this solution with the water sample, which has no color. Mix this, the coloring reagent, you making the molybdenum blue. So that's why it looks something like that. Okay, one of them is blank. The last one is a blank. You always have a blank in it. Okay. All right. Now, after you have all this molybdenum blue, we're ready to measure the absorbance for each standard solution. Put in the cuvette and then add on to the spectrophotometer. Okay, don't just add into the spectrophotometer. You need a cuvette. Okay. All right. Read the absorbance. So let's say you get that. All right. So now we have absorbance right here and all the concentration of the phosphate. You're gonna put this into Excel. Look like that. All right. Now this is what I want you to do. So you have to do this for in the lab anyway. So pause the video right here. Try it out first on your own. I want you to plot copy this data, so absorbance and then concentration, put in Excel, and then plot graph. Okay, remember the absorbance has to be on y-axis, the concentration has to be on x-axis. Right, plot a graph in Excel and get the trend line and then generate the equation on trend line. You done that on the first lab before, okay? If you still remember, exactly like that. Try to get to the molar absorptivity of this equation. Let's try that first, okay? Try to pause the video and do it. All right, if you've done that, you should get a graph like this. Maybe it's not doesn't look like this because I kind of like make it a little bit easier to read, to see, okay? But it looks something like this at least, okay? And if you click on the adding trend line and then generate the equation, you should get that equation, okay? R squared is close to 1, so that's pretty good data, all right? Now the slope, where's the slope? Right there, 2243, okay? So the slope is M right here is molar absorptivity and times length. Length is 1 centimeter, so that's it. So molar absorptivity is the slope, and that's the unit of it. Okay. Now, if you ask me how do I get this unit, well, the slope is y over x. Remember that, delta over y over delta x. Y has no unit, not nanometer, so that's a absorbance at this wavelength, so that's not absorbance, not the unit of absorbance, but the concentration have the unit of molarity. Okay, so that's where you get per molar. The per centimeter come from the length right there. All right. All right, now we're ready now. So how to get to the concentration of the phosphate in the water sample. Okay. All right, so from water sample, we did this already. So add molybdenum blue, wait 10 minutes. So you get, no, I said wrong. Add ammonium molybdate, wait 10 minutes, you get molybdenum blue. Put it in a cuvette, add on to read the absorbance in the spectrophotometer, you get 0.22, okay? And it's molar absorptivity. All right, use the Beer's law, right? So A is 0.22, molar absorptivity is 2243 per molar per centimeter. Length is 1 centimeter, and solve for concentration. Per centimeter and centimeter cancel out, so concentration is that. 2 sig figs, you get 2 sig figs. There we go. That's molar. Okay, but you have to determine the concentration to in ppm, part per million. So you have to convert molarity to part per million. All right. So part per million is milligram per liter. It's the same thing. All right, milligram per liter solution. So it's acceptable unit. So we go milligram of phosphate over a liter of the solution. Right now, we have molarity, which is mole per liter solution, all right? So I'm going to take this number right here, put into right there, all right? Do not use the number that you have been rounded off, all right? If you remember, every time you rounding off a number, you add the uncertainty to the number. So don't do that. Use a raw number right there, okay? So add right there, all right? Now, at the bottom, liter, as you get liter already, all you have to do is convert mole to milligrams, okay? To do that, all right, mole to grams first using molar mass, put mole at the bottom and grams at the top, mole cancel with mole. All right, grams to milligrams, so it's 1,000. 1 gram is 1,000 milligrams, so put gram at the bottom and milligrams at the top, no cancel out. You should get this number. All right, that's a raw number. 2 sig figs, make it 2, so 9.3 ppm. Here we go. Right. You're going to do exactly like this in the lab. All right, you're going to have one water sample. Yeah, I think there are 2. You pick one and make us. We also have the phosphate concentration. Phosphate standard solution for you. There are 6 total. Yeah, not for you. We have a stock for you. You have to do 0 dilution on it. Okay. All right. One more time, just to make sure that you understand how to use Beer's law. Okay, so this one I'll have you practice on your own. I'm not talking about it. All right, so this one basically just use what we learned earlier. I just saw you. No, sorry, I just taught you earlier. Right, how to use it. I'll try on your own right here before you take the pre-lab quiz. Okay, so there you calculate the molar absorptivity first. All right, once you have that, you can determine the concentration of any solution. Basically, all right. I'll pause the key right here. That's for A. And this for B. After you have gotten the molar absorptivity, go for B. Ta-da, that's the concentration. Here we go. Okay. And one more, another skill that you need to be able to do is to convert molarity to ppm. Okay, so take this number right here. So it's a connected question basically. What is the concentration of iron 2 solution in the previous question in part per million or ppm? All right, so we have molarity right here. Again, molarity, part per million is milligram per liter. That's an acceptable unit. Okay, so a molarity is mole per liter. What you have to do, convert mole to milligram. That's it. At the bottom is already a liter solution. All right, mole to grams first. Use molar mass. Put mole at the bottom, grams at the top, and then cancel out. That's a molar mass of iron 2. Okay, and grams to milligrams. So put grams at the bottom and 1,000 milligram at the top. Cancel out. You should get this number. Rounding off, you get 1.8 times 10 to the 4th ppm.